All right, parallel circuits. They're a little bit different and a little bit more complicated, but not horribly. Here are two parallel circuits. Wait, I lied. They're actually the exact same parallel circuit, just drawn differently. That's one thing to keep in mind. Parallel circuits can look different ways. Be careful. Make sure you're aware it's parallel. What makes it parallel? What makes it parallel is the fact that there's a split. There's an option. Current has to choose which path it's going to do. It can't do both. With series, you go one and then the next and the next. It's serial, like a television series. Parallel, you're operating at the same time. Both of them happen. Keep that in mind going forward. Closer doesn't matter. All right. Just like we talked about with series circuits, there are rules. The voltage rule. You guys already all figured this out, I'm sure, from your lab. The voltage rule, the total voltage loss in a section is equal to the voltage in any of them, is equal to the voltage in the other one, is equal to the voltage and so on and so forth. No matter which path I choose, I have to lose the same voltage, because if I gain 9 volts here, and I make a choice, if I lose 9 volts here, I can't lose any here. So I have to have lost all of them when I come back. I have to lose all of them when I come back. Alright? Secondly, the current, though, on the other hand, actually splits. So the total current is equal to the current in one of them, plus the current in the other one, plus any others. It splits, and then it comes back together. Like a river. The amount of water going in can't be different than the water in either branch, can't be different than the water that comes out the other side. All right? Same thing going on here. It joins back up. This one thing. All right. One thing you noticed in doing the lab is that as I added resistors in parallel, the total resistance drops. The equivalent resistance drops as you add resistors. You can kind of think of this back to our rho L over A equation. I'm adding resistors next to each other, like I'm making the area bigger. Bigger denominator, lower resistance. I like to think of it as like lines for people trying to get into a club or a concert or whatever. If you only have one line, a lot of people crowd in this one spot. If I open a second line, it makes it easier for people to get in. The total flow will go up. Any individual flows are the same, but the total flow goes up, and now there's a pressure drop as you go through. You lose your money as you go through the concert. All right? So, what's the rule for this? Well, I'm going to give it to you. First, a challenge. If you can derive it, there's a challenge opportunity at the end of this module. Give it a shot. Turns out, the equation's a little bit complicated. So let me erase the board, and then I'll show it to you. Okay, not the entire board, just this part. The equivalent resistor, well, the reciprocal of the equivalent resistor, 1 over, is equal to the sum of the reciprocals of the individual resistors. That's an easy place to make a mistake. The reciprocal of the resistor is equal to the sum of the reciprocals. Be careful with that. All right, let's do an example. All right, let's try an example problem with parallel circuits. So here we have an 18-volt battery and 3 resistors in series. All right, let's try an example with a parallel circuit with an 18-volt battery and 3 resistors in parallel with each other. So, questions. What's the voltage of each resistor? What's the current through each resistor? What's the equivalent resistor? And what's the current to the battery? Let's start here. This is actually really easy. They're all 18 volts. Because I gain 18 volts, and then when I get to this point, I have to make a choice. And whichever choice I make, because there's no other resistors in that choice, I lose all 18 volts in that leg of the parallel circuit. So no matter what, it's all 18. Well, let's talk about currents. That's really easy too. I can just do V equals IR. And I know V, and I know R for each resistor. So it's 12 equals 18 equals I times 12. 18 equals I times 6. 18 equals I times 3. Or 1.5 amps, 3 amps, and 6 amps. That's really easy. Equivalent resistors are a little bit more complicated. Just keep in mind, we're using a reciprocal is equal to a sum of reciprocals. Alright, you can do this with a calculator, or you can just do a little bit of common denominators. Does that mean my equivalent resistor is 7/12 of an ohm? No, because that's equal to 1 over Req. The equivalent resistor is 12/7 of an ohm, or about 1.7-ish. Don't round yet, because we still got to talk about the total current, the current through the battery, the current after these all combine back together. We actually have two ways of doing this. One, we can say, well, V equals IR for the equivalent circuit, which is just, we have a battery and a resistor. Alright, that's really easy to do. 18 equals I times 12/7. I is 10.5 amps. But there's another way to do it. We can look at all three of these currents and say, oh, they all have to combine together to get in there. 6, 3, 1.5. Oh, that's also 10.5 amps. That's pretty cool. It works, whichever way you go. Okay, 2 parallel problems. Nope, try that again. Okay, 2 more problems for you to try on your own. First one, parallel circuit, unknown battery, 10 ohm, 6 ohm, unknown resistor. The current to the 10 ohm resistor is 1.5 amps. The unknown resistor is 2 amps. I want to know what's the voltage of the battery and what is the unknown resistor. Second question is a combination of both series and parallel. I'm going to take 3 resistors, 50 and 2 unknowns. I'm going to build a series circuit. The total resistance is 100 ohms. And then I'm going to build a parallel circuit with the same resistors, total resistance of 30 ohms. I want to know, what are the unknown resistors? Give that a shot. Those are your 3 problems. The one from the series circuit and these 2. Give it a shot. Turn those in. That's your assignment for the day. Bye, everybody.